Hi guys, so today I'm here to present um, the AP Calculus BC free response question. Today we're going over to the BC only part of the calculator section to tackle the first polar question in 6 years, 2025 BC 2. So in this question, we're given two polar curves that we'll graph right away. First, we have r of theta equals 2 sine squared theta. So this is our main curve that we'll use for most of this question. We'll see it here. We're only going to use the top half though, because we're given a domain 0 to theta to pi. And that's the curve we're going to use here. And we're also going to use r equals 1 half. This is a red curve that we're going to see. So by the way, this black thing is curve C. The red thing is the semicircle. We're also going to round this to pi to make a semicircle, not a full circle. So now here, the first thing we're going to do is we have part A. So part A is asking for rate of change of r with respect to theta. So with the standard mathematical notation, this would equal dr over d theta. So all we have to do is take dr over d theta of r of theta, or we're going to differentiate 2 times sine squared theta at 1.3. And this would give us a part A answer here. So we're just going to do dr over d theta. Yeah, no. So dr over d theta. So to take the derivative of this, we're going to do r of theta. So this would be r prime equals. So this would be 4 times sine of theta times the derivative of what's inside, which is cosine of theta. And then at theta equals 1.3, we're going to do r of 1.3. And there's our answer we do get here. And then, yeah, based on our answer here, we got a derivative here. And we're going to keep this because we'll need it later. So here you'll see it's 1.031. So answer, we're going to say from calculator, part A answer equals 1.031. That's a pretty easy point. I'm assuming that part is only going to be worth 1 point. Part B. So now we're going to get a classic question where it's going to ask us for the area between two polar curves. So we need the area inside the big curve but outside the semicircle. So first we need to find where they intersect. So we're going to set these two things equal to each other. 2 sine theta equals 1 half. Sine squared theta equals 1 over 4. Sine theta equals 1 half. And this, of course, means within 0 to pi, this is going to equal theta equals pi over 6, and theta equals 5 pi over 6. So these are our limits of integration. And remember that the polar area formula equals 1 half times the integral between alpha and beta of r squared minus r squared. This is like outer minus inner, okay? It's just like area between curves, or you think of it like the Marshall method where you separate them, square individually, and subtract the theta. So we're going to plug this in here. We know the limits of integration. So we're just going to do 1 half times the integral from pi over 6 to 5 pi over 6 of r of theta squared minus 1/4 d theta. Alright, so we're going to change this to s of theta just to be careful. And here we're going to change to s of theta and put here. And there we have our answer. We defined it as to differentiate, and this will calculate the area properly for us. So don't know what happened here, but it ruined our graph. This is fine though. Yeah. So yeah. No, we're just going to say two sine squared of theta, and yeah, we still got our answer back. So I'm going to copy paste the setup. This should be fine, and we're going to say area equals this, and this is our B answer. So part C, we're going to need a maximum x coordinate of the polar curve. So we're given this function for dx over d theta. So we've done a lot of function analysis questions before, and we've done way more than enough of them to know that the maximum will occur when dx over d theta equals 0 and changes sign from positive to negative. This came up on the last part of BC1 or AB1 if you're taking AB, and self-studying BC for maybe a future year, or maybe you're taking delayed exam and wants to review BC content. Who knows? I'm here to support you no matter what. So now we're going to plug in our dx over d theta. We're going to say another. We're going to do another r equals. No, we're just going to do 4 sine x cosine squared x minus 2 sine cubed x, and this is going to be oh wait, yeah, we're going to have to do this the hard way because we don't support more or higher powers. We're going to do this, and now we're going to find where it's 0 from the interval 0, 1, and we find this happens at 0.955, and it does turn from positive to negative here, so we're good. And this theta, and it is inside our domain, so we're good here. And it's a closed interval. I'm going to include this, and this is the part C answer. And finally, part D. I've seen a lot of people overcomplicate this one and use related rates. Alright, here's where the chain rule or Leibniz notation comes in handy. It's coming in handy with the chain rule, it will come in handy here. It will oversimplify the process a lot. So watch this. We're given d theta over dt, and we know what dr over d theta is. We've calculated it here. So we're trying to find the rate at which the distance from the origin, or r, is changing with respect to time. Guess what? This can be represented by dr over dt. So now we look at this relationship. dr over dt equals dr over d theta, which we already know, times d theta over dt, which is given. So all we need to do is multiply these values out. This is from part A, and we're given 15, and we will get 15.465. And this is the answer. So all it takes is you can do it in a clever way and do this. And it is a quick part D to end off the calculator section. So the note is, don't give up immediately when you see polar. You're going to be able to get some easy points. Just remember 1/2 r squared d theta. The integral of from alpha to beta of r squared d theta is the area, And remember the derivative formula, which you didn't need here, but you need on some other thing probably if you're taking the late exam or next year if you want if polar comes up again. So the good news is, even though you got a polar, this is a relatively straightforward polar question. There was nothing too out of the ordinary, and there were a few things that were the same as non-polar functions. So see you in the next video where I'm going to start covering the non-polar section and the non-calculator section. Yeah, there's also no polar, so I guess that description's right. But we're going to cover the things that are guaranteed to come up each year, the table and graph questions, which came up on both the AB and BC exams.